All right, welcome to Physics 360, Chapter 2, Sections 1, 2, and 4, Velocity-Dependent Forces. Okay, so we're basically going to start off with Newton's laws. So we have the first law: an object in motion or at rest will remain in motion or at rest unless acted on upon by an outside force. Newton's second law, which tells us the rate of change of momentum has to be the net force acting on the system from outside the system, and if mass is constant, then we can write the rate of change of momentum, where momentum is mv. We can write it as m times the rate of change of velocity with respect to time, and then that will be equal to the net force. All right, so let's do a constant force example. Let's say we have some mass m falling down on the earth. I make the positive direction down. So this is what happens with Newton's second law. So our net force is just the weight force, which is equal to mg. The masses cancel, and we get our rate of change of velocity is equal to g. And then since they're all pointing in the same direction, I don't need to pay attention to the velocity anymore. I'll just use the scalars. And so this is a separable differential equation as is. If I integrate both sides, I get b of t is equal to gt plus some constant. And then I can plug in the value that knowing the definition of velocity is equal to the rate of change of position, in this case the x variable. I can plug in for what v is. Again, it's a separable differential equation, so I can integrate both sides, and voila. I get 1/2 gt squared plus ct plus c1, where c and c1 are constants of integration and are based on the initial conditions. So let's say the initial conditions is velocity is equal to 0 and x equal is 0. And if we do that, we put in a t equals 0, velocity equals 0, so we get this. So c has to be equal to 0. And then that makes the x equal to this. And then if we plug in the initial condition for x, that's going to force c1 to be equal to 0. And then we get our solution for our rate of change of velocity to be this, or our velocity function to be this, and our position function to be this. All right, so let's go into a velocity-dependent force example. So what we're going to do is add the same system we had before, except I'm going to add a drag force pointing opposite of the motion. That's why it's a drag force. And what we're going to say is that our velocity force can have two components. It can have one that's proportional to velocity, which is this linear component, and then one that's proportional to v squared, which is its quadratic component. Then what we're going to do is set up Newton's second law again. So we have two forces we have to deal with. So if we plug in what they are and then divide by the mass, we get this equation for the rate of change of velocity. Except the problem is this problem is difficult to do. So what we need to do is make a simplifying assumption, and the way we do that is we look at this ratio of the quadratic term divided by the linear term. And let's talk about what C1 and C2 are. Those are constants based on the shape and size of the object that is falling through the fluid or gas. That depends on the object that is falling. And we would have to look them up or do experiments to determine what C1 or C2 are. All right, so let's look at this ratio. So if the linear term is dominant, that means that this ratio should be less than 1. If they're both about the same size, then it would be approximately equal to 1, and we'd have to include both terms in our force. Or if the quadratic force is dominant, then this ratio is going to be much greater than 1. So we can look at this ratio and determine which of the drag force components will be the largest, and then we'll solve that system. So let's assume the linear force is dominant and that ratio is less than 1. And what we get is this differential equation to solve for velocity, and it is a separable differential equation. I can separate it this way, and then I can solve the integral on both sides by using this substitution, and that gives me my differentials for that substitution. So if I plug them into my integral, I get this integral. Let's simplify a little, and then the integral of u du, or the integral of du divided by u is equal to log of u, and then I get an integration constant that I call d. I plug back in my substitution, and this is the solution to the differential equation that we have to deal with. So now I need to solve for v. I multiply by a minus c1 over c1 over m on both sides, and then I take the exponential of both sides, and then I solve for v, and then solve for v again. And this is my function of v of t that I get. It is represented in this form. Now we have to find our constant d. So I need to apply my initial conditions, the same initial conditions that I applied in the constant force problem, which is that the velocity is equal to 0 at t equals 0, and the position is equal to 0 at t equals 0, and positive is still pointing down. Alright, so that's my equation. I have solved for the velocity of this object. And let's talk about this differential equation we're solving to get this answer. It's that. Let's assume time has gone on for a while, and you can see from my picture that the drag force has gotten larger, so much larger that the two forces are equal and the velocity is no longer changing. We are at constant velocity. And if we solve this system for the velocity at which it reaches, and we do that, that's called terminal velocity. That's the maximum, in this case, the maximum velocity it can obtain. Alright, and we call that terminal velocity. Now let's solve for this integration constant d. You can see in my expression I have terminal velocity already there. We have an mg divided by c1. And now I can put in my initial conditions. At t equals 0, velocity equals 0, and if at t equals 0, the position equals 0. So let's plug that in, and we get this solution. We need to solve for the d constant, so I have to bring the exponential term over to one side, multiply by c1 divided by m. And remember, what is terminal velocity? If I plug that in there, and so that term on the left-hand side just equals g. Now I can take the logarithm of both sides to get rid of the exponential, and now I can solve for d. So what I'm going to claim is my integration constant is equal to this. So I'm going to plug that back into my solution, and then apply a property of exponentials, or exponents, so that they have a sum. And let's simplify the terms. You can see the mass in the c1 cancels, and I'm just left with log of g there. Now let's apply the property of exponents to the exponential term, and I get this, where e to the log of g is just equal to g. And look at that, I get a terminal velocity term that pops up, multiplied times my exponential function, so I can factor that out front. And this is the solution for the velocity that I get here. Now, since the velocity is just a function of time, it's fairly straightforward to set that equal to the change in position divided by the change in time, and then integrating that and getting a value for position. But I'm going to leave that up to you. I'm going to go and do a solution for drag, for quadratic drag. So this is, from Newton's second law, we get this equation this time. And then we're going to solve that by integrating both sides. It's a separable differential equation again. And then let's look at the terminal velocity case before we move on. If we do that, we find out that terminal velocity is equal to the square root of mg divided by c2. And c2 is the drag coefficient again. Again, that depends on the shape and the fluid we're going through, the shape of the object falling, and the fluid that we're going through. And we can experimentally determine C1 if we need to. I am going to factor out a G for this region, because if you see this term on the bottom, the C2 divided by mg, well, that's the reciprocal of the terminal velocity squared. And if I put that in there and factor out a g and move it to the other side, I have this integral to solve. And this integral shows, oh, it looks like I didn't square the terminal velocity on the bottom of that expression. That should be squared. I apologize for that. So what we're going to do now is look at the integral tables to solve this integral. And if you look, it turns out to be inverse hyperbolic tangent. And then we can take the hyperbolic tangent of both sides and get this expression. So this, and now we can apply our initial condition. So if we do that, I get this expression for hyperbolic tangent of d. Well, what is hyperbolic tangent? Well, you look at this graph, the only way the hyperbolic tangent goes to 0 is when x is equal to 0. You can see that. So that's going to force d is equal to 0. And then so my solution for this differential equation and the velocity of this object falling in quadratic drag is equal to v of t, and the terminal velocity, times hyperbolic tangent of gt. Well, that's it for velocity-dependent forces. I hope this gives you a better idea on how we can solve velocity-dependent forces using Newton's law and figuring out a velocity term and then using that to get a position term. This is the end of this podcast, and I will talk to you later. Bye.